In this video, we're going to look at a very special family of infinite series, and those are called the p series, which will always have this form, 1 over n to the p. And if p, what this theorem says is that if p is bigger than 1, then that series will converge. If p is less than or equal to 1, then the series diverges. So we're going to kind of ground our understanding. We're going to use this as the root of our understanding for other series, and they become very useful when we want to do comparisons. And the other thing I'll note is that if p equals 1, then we just get the harmonic series. Which we proved in the last video. We showed in the last video that diverges. Okay, but let's see the type of comparisons and problems you'd want to be able to do using this family of infinite series. Okay, in each of these problems, there's a point I want to make in terms of the things you can assume. So for instance, if we want to determine the convergence and divergence of the series here in part A, one thing you can do is you can take the 4 out. So that equals 4 times this infinite series. And we've already seen that that's the harmonic series which diverges, but if we treat it as a p series, we see that this is p equal to 1. And so therefore, that diverges, okay, by the p series test. So that 4, obviously that 4 makes no difference, right? If that series there is infinity, then 4 times infinity is infinity. If it converges to some number, whatever that is, then it would just be 4 times that number, and we would say it converges. So part B, similar idea, we can take out the negative 64. And I get 1 over n squared. Now, this is a p series in which p is equal to 2. And by the p series test, that tells us that that converges. Right? And again, the negative 64 would just be multiplied by whatever that infinite series is. Part C, again, we can take out that negative 8. Right? And just to show you that this is even if it's only slightly over 1, the rule is still the same. So p is equal to 1.00001, which of course is bigger than 1. Maybe I'm going to just state that just to remind you in both these cases. So that implies that that is going to converge. And part D, the point I want to make is that this, if you notice, this series starts at 4, which basically means that we're just missing, let me zoom in on it here, or at least move these out of the way. So the point I want to make is that this is missing. If you think about what it's missing the 1 plus a half plus a third. But that's not going to make any difference in terms of the behavior of the overall series, right? If you just get rid of a finite number of numbers, it's not going to change whether this infinite series diverges or converges, because that behavior is determined by its long-run behavior. Okay, so this is, of course, this is 1/4 plus a fifth. It's the same as the harmonic, but it's missing those first 3 terms, but still, we treat it like a regular p series, and that's going to diverge. Okay, so a couple of nuances really don't change the overall approach. Here are a few more examples which tend to confuse some students. So let's just do a few of these examples. The first thing I would notice about E is that you can rewrite it, right? So this is the same as if you just cancel out some of those n's, you get 1 over n squared, right? And so that's a p series in which p is bigger than, or p is equal to 2, and that's bigger than 1. So this converges. You want to be able to rewrite radicals into exponential form. So I would write this as 1 over n to the 2/5, right? And of course, p in this case would be 2/5, which is less than 1. Or I should say less than or equal to 1. So therefore, it diverges. You want to use property of exponents appropriately. So I could write this one as n to the 1/5 divided by n to the 1/3. And then, of course, we could write that as just subtracting those exponents. So I'd have to do a 5th minus a 3rd. So a 5th minus a 3rd, that's the same as 3/5. 3/5 minus 5/3. Right, and 3/5 minus 5/3 is negative 2/3. So this would be n to the negative 2/3. Negative 2/15. That's what I meant to say. Let's try that again. 1/5 minus 1/3 is the same as 3/15 minus 5/15, which is negative 2/15. And I could rewrite that, of course, like this. And 2/15 is our p-value, and that is less than or equal to 1, so that implies that this diverges. Okay, and then in this last example, of course, we can factor out that 4 there. It's not critical to the behavior. I can write this as, n to the square root of n, I can write that as n to the 1/2, and the cube root of n is n to the 1/3. Now, a half minus a third ends up giving you 1/6. So this ends up being 4 n to the 1/6. Right? And not to the negative 1/6, just n to the 1/6. So it's quite obvious that this is going to diverge because you're just adding up the 6th root of 1 plus the 6th root of 2. Those are all numbers that are bigger than or equal to 1. So you're adding up a bunch of numbers bigger than or equal to 1. So that diverges. You could write it like this to be if you really strictly wanted to use the p-series test. That's also the same as that. And then clearly p is negative 1/6, which is less than or equal to 1, so it diverges. Right, so these are all applications of the p-series in disguise, and again, they're very good. These are very good series to know because you end up using them to compare to other series that you don't know, and there's something called the limit comparison test, which we'll be seeing in the future, and that'll allow you to and having these as sort of like your series to compare to will make those problems much easier.